So we are back to work, and our next speaker is Lucyshyn Wright, and he'll talk on algebraic dual adjunctions and bifold algebras. Okay, Rory, you may
Thanks
start.
very much. I wanted to start off by thanking the organizers for this very well organized hybrid conference. It's very impressive, and a lot of work goes into making that happen. Thanks very much. Okay, so I'll start off. The title of the talk is Algebraic Dual Adjunctions and Bifold Algebras, a Bi-Equivalence. And so, as the title suggests, in this talk, we'll describe a bi-equivalence, in fact, between two categories, and the objects of the two categories are respectively algebraic dual adjunctions, which are contravariant adjunctions between algebraic categories, and on the one hand, and on the other hand, bifold algebras, which can be described equivalently as commuting pairs of algebra structures on the same set or object. And we'll be working in a general setting for categorical universal algebra. And so that's the first thing that I'll talk about. So to introduce the setting that we'll be working in, we'll start with just a symmetric monodal closed category V with just finite limits. And then we'll consider categories enriched in V, but I'll still call them V categories. And then in addition, we'll ask for what's called an eleuthertic system of arities, in the sense of my paper in TAC called Enriched Algebraic Theories and Monads for a System of Arities. And so what an eleuthertic system of arities is, well, it can be described equivalently as a full subcategory J of V, and it doesn't have to be small. It's a full subcategory J of V that contains the unit object and is closed under the monodal product in V. So that's a system of arities, and then we require that it be along that inclusion, first of all, exist, and sorry. So first of all, enriched left conextensions along that inclusion exist, and secondly, are preserved by homming out of every object of J in enriched sense. Okay, so given these data, we can look at generalized Levere theories, generalized with respect to this given system of arities. So in particular, a J theory, as it's called, is a V category T equipped with an identity on objects V functor going from J op to T that preserves J cotensors. So an example of this is if V is the category of sets and J is the category of finite, full subcategory of finite cardinals, then for that system of arities, a J theory is precisely a Levere theory in the usual sense. And then we can form the category of J theories with an evident kind of morphism. And so we'll use this notation TH sub J for the category of J theories. And then, given a J theory T, we can consider T algebras for that J theory. A T algebra is a V functor A going from T to V that preserves J cotensors. And then we'll define the following terminology as well. We then call the pair T comma A an algebra, so that an algebra is a T algebra for a specified associated theory T. We call these algebras. And T algebras form a V category, even though we didn't assume that J is small or that V is complete. We only assume that V has finite limits, and yet it's still the case that the V category of T algebras exists. That's because we can use equalizers to form it, and it's possible to do it with just equalizers. Okay, so we have this notation T-alg, and actually it's functorial contravariantly in T. So we get a functor from the opposite of the category of J theories to VCat, and then we can post-compose with the forgetful functor to cat. We get a cat-valued functor, and this cat-valued functor then determines a split op vibration, which we'll write in the following way. So we're introducing notation here, alg, for the category that we get. And its objects then are algebras, T comma A, and the resulting op vibration sends the algebra T comma A to the theory T. Okay, there are, of course, so this alg then is a category of algebras over various theories. And of course, there are other such categories that we can consider. But this is the one that we end up needing in this talk. Actually, more so, we'll need a variation on this using a similar process for a slightly different kind of structure, but we'll see that soon. Okay, now we can form the category of T-algebras. So using this idea, we can make the following definition. A J-algebraic V category is a V category A equipped with a V functor down to V such that A is equivalent to T-alg in the pseudo slice 2 category over V in VCat for some J theory T. So we have the notion of J-algebraic V category. Usually I call these J-algebraic V categories over V because I have a specified V functor down to V, but for brevity, we'll call them J-algebraic V categories. And of course, we can form a 2 category of these, a full sub 2 category of the pseudo slice 2 category. So we have algcat J, the 2 category of J-algebraic V categories. And we can prove that the functor that sends each J theory T to the category of T algebras, considered as a J-algebraic V category, this is actually a biequivalence between the locally discrete 2 category theories J-op and the 2 category of algebraic J-algebraic V categories. Okay, using well-known ideas. The semantics functor here co-restricts to a biequivalence. Okay, so now one of the main concepts in the talk, but perhaps not the most central concept, which we'll see later, the concept of J-algebraic dual adjunction. But first, we have another important concept for this talk. Given J theories T and U, a pair of theories, then a T comma U algebra or a TU algebra is a V functor D going from the monoidal product, usual monoidal product of V categories T tensor U to V. So it's a bifunctor, V bifunctor that is required to preserve J cotensors in each variable separately. And in a moment, we'll see various, a couple of equivalent descriptions of these that are perhaps a little bit more, or perhaps more familiar. But for the moment, let's observe, I'll introduce another important definition for the talk as well. So we'll call the triple consisting of the theories T and U and this TU algebra D, we call this a bifold algebra. So a bifold algebra is a TU algebra for a specified pair of theories T and U. Okay, and we can observe that every TU algebra D determines, firstly, a T algebra on the one hand by plugging in the unit object I of V, which actually sits in J. We can plug that into the second argument and we get D blank comma I. This is actually a T algebra and we call it the left face of D. And then similarly, we get a U algebra D I blank called the right face of D. So every TU algebra has an associated T algebra and an associated U algebra called the left and right faces of D. Okay, there are some equivalent descriptions of TU algebras. Up to an equivalence, a TU algebra may also be defined as, firstly, a commuting pair of T and U algebras. So those are T and U algebras respectively on the same carrier object that are required to commute in a certain well-known sense. So that's an equivalent description of TU algebras, in fact, up to an equivalence. And then secondly, we can describe TU algebras also as algebras for the tensor product of J theories, T tensor sub J U, if we can form that. So in particular, if J is small and V is locally bounded, which we don't assume in this talk, then we can certainly form the tensor product of J theories. And the algebras for this are equivalently described as TU algebras. Okay, so this is, of course, building on well-known ideas. And of course, so the root of many of some of the ideas in this talk is the paper of Fried called Algebra Valued Functors and Tensor Products in particular. Okay, so now we can actually form a V category, TU-alg, V category of TU algebras. And we can do this even though J isn't small and we don't assume V is complete. At the end of the day, we still indirectly can use the equalizers. But in fact, to show that this V category exists under these weak assumptions, we actually have to first show it's equivalent to another category of commuting TU algebra pairs. And then that one exists as a V category, and this, as a consequence, exists as a V category as well. This notation is functorial in T and in U, so we get a contravariantly, and so we get a valued in V cat, which then yields a functor valued in cat, and so we can, this determines an opt vibration again, using the same sort of method then, which we'll write in the following way. So we're introducing a notation here, B-alg, for the category that we get by applying the relevant kind of Grothendieck construction here. So the objects of B-alg are going to be bifold algebras, a pair of theories T and U, and a TU algebra D. And then the given opt vibration sends the bifold algebra to the underlying pair of theories, T and U. Okay. Now this brings us to one of the main concepts of the talk, the concept of J-Algebraic dual adjunction, which I have spoken about at an earlier CT conference. At the time I called them J-Algebraic dualities. The term being used here now is J-algebraic dual adjunction. A J-algebraic dual adjunction consists of, first of all, a pair of J-algebraic V categories V and a V adjunction of the following form. So a contravariant V adjunction between these two V categories. So in other words, a J-algebraic dual adjunction is a V-enriched dual adjunction between J-algebraic V categories. And we'll use this notation. And what we'll do is we'll form a two category whose objects are J-algebraic dual adjunctions. And we'll write this as ADA sub J, the two category of J-algebraic dual adjunctions. And in there, the one cells can be described in the following way. A one cell of the form depicted would consist of, as indicated below, a pair of one cells in the two category of J-algebraic V categories, so P and Q, together with a two cell of the given form in V cat. And also we can take mates to express that also in terms of the nablas instead of the deltas, the right adjoints instead of the left adjoints. Okay, so we get a two category of J-algebraic dual adjunctions. And what we'll do in this talk is form a biequivalence, show that there's a biequivalence between J-algebraic dual adjunctions and bifold algebras. And that is the first of the main theorems here, which we have on this slide. So first of all, there is a biequivalence between the locally discrete two category of bifold algebras on the left. So that's just an ordinary category. And then on the right, we have the two category of J-algebraic dual adjunctions. So that's the main statement of the theorem, but equally interesting is the description of how it acts on objects. So under this equivalence, each bifold algebra, T, U, D, is sent to what I call its dualization adjunction. So this is a contravariant adjunction or dual adjunction between T-alg and U-alg, and both the left and right adjoint are given by homing into D, that bifold algebra. So D is an object of V, in effect, that carries both a T algebra structure and a U algebra structure that commute. And we can actually show that there's an adjoint pair of functors of this form, both given by homing into that same object D. And this is how the biequivalence acts on objects. Every bifold algebra corresponds to its dualization adjunction in this way. And of course, from this, we get several corollaries. You know that every J-algebraic dual adjunction is equivalent to one of this form, and that's for an essentially unique bifold algebra TUD. Okay. We'll explore some corollaries of this, where we'll look at special properties of bifold algebras on the one hand, and corresponding special properties of J-algebraic dual adjunctions. So a bifold algebra is said to be left commutant if, when we take its transpose of the following form from T into the V functor category from U to V, will require that this be fully faithful. And then we say that the bifold algebra is left commutant. Similarly, we can define the notion of right commutant bifold algebra, taking the other transpose of D and requiring that it be fully faithful. And then if we have both properties, then we say that it's a commutant bifold algebra. This is one equivalent characterization of these notions. I'm giving this definition because it's very quick to state. But we can also, the reason for the terminology is that a bifold algebra is left commutant if its left face is the commutant of its right face. There is this theory of commutants for enriched algebraic theories, which I've developed. And so the requirement for, in particular, for a commutant bifold algebra is that each of its faces is the commutant of the other. Okay, now a corresponding property of J-algebraic dual adjunctions. If we have two J-algebraic V categories and with associated J-algebraic V adjunctions like this, but that exhibit them as J-algebraic V categories, then a J-algebraic dual adjunction between them is said to be left stable if whenever we take F at J, the free object on J, for an object of the subcategory of arities, system of arities J, will require that it be reflexive in a certain sense with respect to the adjunction. In particular, this means that the canonical morphism that you see there from F of J into nabla of delta of F of J is required to be an isomorphism. And similarly, we say that the J-algebraic dual adjunction is right stable if all the free J-generated objects in B are reflexive with respect to the dual adjunction in this sense. And then we say that it is stable, a stable J-algebraic dual adjunction, if it is both left and right stable. And now we'll see that these properties correspond to the properties of bifold algebras that we've just seen. So in particular, we can state this in the following way. The biequivalence between bifold algebras and J-algebraic dual adjunctions restricts to a biequivalence between, on the one hand, left commutant bifold algebras, and on the other hand, left stable J-algebraic dual adjunctions. And we have similar results for right commutant and right stable, right commutant bifold algebras and right stable J-algebraic dual adjunctions, similarly commutant and stable. So we have these restrictions of the biequivalence. And we'll go further with this because there's a sense in which a right commutant J-algebraic dual adjunction, well, actually, let's approach it the other way. A right commutant bifold algebra is uniquely determined by its left face, because the right face has to be the commutant of the left face. So actually, we can reduce to just a single algebra in a certain sense that we'll see. To do this, we'll need the notion of commutant for algebras. If we have an algebra T comma A, then it determines another algebra T A perp, called the commutant of T A. And here, the theory that you're seeing there, T perp sub A, is the commutant of T with respect to A, which also is the J-algebraic structure of the V functor A, going from T to V, the given algebra. And we say that the algebra is saturated if the canonical morphism from T into its double commutant is an isomorphism. So we have the notion of saturated algebra. Okay. So a further thing that we'll need is that every algebra TA actually determines an associated right commutant bifold algebra. And we'll write it in the following way: R com of T comma A. It's a bifold algebra, so it has two theories. In this case, they are T and the commutant of T. And then we can describe a certain T perp A algebra here. The key thing is that the left and right faces of this bifold algebra are T and the commutant of, T comma A and the commutant of T comma A respectively. And in fact, you know, a bifold algebra is right commutant if and only if it's isomorphic to one of this form. As we've said, right commutant bifold algebras are those whose right face is the commutant of the left face. Okay, we'll actually need some more notation as well. So some of the categories we've seen, to state our final results, we'll need to pass to the groupoid core of some of these categories. So here we'll take the groupoid core of the category of algebras. This has the same objects as the algebras, but we'll take only isomorphisms between them. So this is a groupoid. We can take the full subcategory consisting of saturated algebras. So we have sat-alg. But then on the dual adjunction side of things, we have two categorical structure. What we'll do is instead take the bi-groupoid core. So specifically...
Sorry to interrupt you, but you should finish in 1 minute.
Okay, yeah, no problem at all. Thanks for the reminder. So here what we are doing is first taking a full sub-2 category of J-algebraic dual adjunctions consisting of the right stable J-algebraic dual adjunctions. But then from there, we're taking what we call the bi-groupoid core of that. So we're taking only as one cells, we take only the equivalences, and as two cells, only in the invertible two cells between those. So this is a bi-groupoid, or in a sense, a two-groupoid. It's a two category where all the one cells are equivalences, all the two cells are invertible. Similarly, we can form a two category bi-groupoid of left stable J-algebraic dual adjunctions and also stable J-algebraic dual adjunctions. And with these notations, we can state our final results. First of all, that there's a bi-equivalence between just algebras and right stable algebraic dual adjunctions, under which an algebra T comma A is sent to the following dualization adjunction involving T-alg and T perp sub A-alg. And this is the dualization adjunction of the bifold algebra R-com TA. Its face is being A and A perp. So we get actually on the left-hand side, we're able to reduce the structure to just algebras, and we get an equivalence between algebras and right stable algebraic dual adjunctions. But then we can go further. Similarly with left stable as well, we get a similar biequivalence. The final theorem that I wanted to state is that this very biequivalence restricts to a biequivalence between saturated algebras and stable J-algebraic dual adjunctions. In a saturated algebra, the left and right faces are, in a saturated algebra, the algebra is the commutant of its commutant. So a saturated algebra corresponds to a commutant bifold algebra where each of the faces are determined, each face is determined by the other. But analogously, on the algebraic dual adjunction side of the picture, we have correspondingly stable J-algebraic dual adjunctions, where in effect the A and B in the dual adjunction are uniquely determined by one another and the structure of the given structure up to equivalence. So we get a biequivalence between saturated algebras and stable J-algebraic dual adjunctions, and also the other biequivalence that we've seen with left stable algebraic dual adjunctions restricts actually to give a similar biequivalence as well. And that brings us to the end of the talk. Thanks very much.
Sorry. Yes, okay. So I'm afraid there's no time for comments, but there was a comment during your talk. Maybe you can very briefly tell us which inspiring examples you had in mind.
Right. So yeah, we have a question in the chat from Paul Taylor. So there are many examples. I'll run through a few of them. So basically, one leading example is
very shortly, but just one example. Yes,
for sure. Yeah. So one leading example is R modules for a ring R, and then so left R modules for a ring R, and then right R modules for a ring R. We can dualize by homming into R. So that's a simple example. That example can be done with arities, just the terminal object. Okay, but it can also be done in terms of the usual finite arities. And then from there, we can look at variations on R modules. We can look at R affine spaces.
Okay, it's time to stop. We have to
okay, yeah, thanks, no problem. Thanks very much.
Careful with time. So thank you. Thank you.
Thank you.